Okay, so let me start by reminding you a little bit about what we did last time. So we start with a quiver, and we want to relate it to, say, Kac-Moody algebras. So we have level 0, and that's just saying that K0 of the category of representations of the quiver with the Euler form, a symmetrized Euler form. This is the same thing as the root lattice. Okay, root lattice of the corresponding Lie algebra with the Cartan form. Okay, Cartan form. And for yesterday, I was a little bit, I wrote something. You should not take the numerical Grothendieck group. You kill maybe too many things when you have isotropic roots, let's say. So you should just take z to the I. Okay. Okay, so that's level 0. It's just purely numerical. And then we have, we saw two things on level 1. Level 1 and level 1 prime, let's say. Well, let's just say level 1. So we have the whole algebra of the category of representations of the quiver over FQ. And, well, this contains the positive half. Let me just write U plus just to make sure then. U plus G of the corresponding Kac-Moody algebra. Okay. And this corresponds to, okay, no, and then we can do something a little bit more fancy. We consider the stack of representations of Q over maybe FQ, FQ bar, or C. And then we consider perverse sheaves on that. And out of these, with the induction diagram, we define a certain category of semi-simple complexes defined by Lustig. And then we take the Grothendieck group of that category. So let me write K. This is, let me just say, this is the graded Grothendieck group of the category Q. And this is Lustig perverse sheaves. Let's just say like that. Okay, semi-simple complexes would be more appropriate. And this is isomorphic to U plus Q1 half of G. Okay? And these two, this and this, they somehow correspond to the constant term of the Katz polynomial. Okay? This is the Katz polynomial. Which is counting indecomposable representations of your quiver. So, so a natural question then is what corresponds what algebraic structure corresponds to the entire Katz polynomial. Okay, and in order to see that, we have to go to level 2, which is where the Kohas begin their life, let's say start to live. And so now we have to consider, T star of the stack of representations of the quiver. And we have to consider the homology and maybe equivariant homology for some torus action of this stack. And this is the Koha that I'm going to talk about today. Okay, and so this will, first of all, it's very natural. I tried to explain that yesterday with the characteristic cycle map. You can naturally construct a map from this graded Grothendieck group. maybe a specialization, you lose the quantum parameter, to something inside of that, okay, the Lagrangian correspondences, not correspondences, the Lagrangian cycles, and this will be strictly bigger, okay, so it's a bigger algebra than the one that arises here, and I will maybe not have time to talk about it today, but this algebra is also important because it will naturally act on the homology of many symplectic varieties that are of interest, namely these Nakajima quiver varieties. Okay, but I will not really take that point of view today. Okay, so the aim for today is to define this thing and also a certain nice Lagrangian substack, and to define the Coha, okay, and then to say what we know, okay, give results on the structure of these Cohas, okay, and maybe at the end, if I have time, I will try to explain how we can hope to transport all this work that we did from quivers to another category of global dimension 1, which are the category of coherent sheaves on smooth curves. Okay, and so there the picture is not yet as complete as it is here, but there's some progress. So. Okay. So let me start by construction of, let's say, some words about constructing this T star rep dq. Okay, so rep dq, let me remind you, is a global quotient stack. So it is a vector space ED quotient by a group GD. Maybe I just rewrite it quickly. ED is going to be the direct sum for all edges. E is, so Q is IE. Okay, I only know 3 letters, I, E, and Q. So you have to deal with that. So this E is the set of edges. This E is the representation space of dimension D. And so it's hom k to the d starting of E, k to the d target of E, and GD is just a big product of GLDIs. Okay. So it's a vector space quotient by a product of GLNs. So a priori it's pretty friendly. And in particular, we can understand the tangent complex. So the tangent complex to point X. Let's say, let me denote a point X, a collection of elements here, a point X. Rep dq. So it's GD, the Lie algebra of big GD, to ED. And here, this is a map, let's call it A. And what is this map? Well, it's just the infinitesimal action of the group GD at the point X on ED. Okay, so it's just the infinitesimal action of the conjugation action. And so I will probably get the signs wrong, but let's denote by yi the collection of elements in G, and X. So this will be something like XE y starting of E minus y target of E XE. Okay, so that's the tangent complex, and so the cotangent complex at the point X, rep dq, this is just a dual of that, and so it's E dual to GD dual. Okay, and so this is A dual. And now you can identify this with the representation of the, I should have put the notation before, but okay, we have to identify the dual of the vector space ED with, again, a vector space, but of representation of a quiver, but now using the trace bilinear form, we can identify the dual of that space with a hom in the other direction. So it means that we're reversing all the arrows of the quiver. So maybe, okay, let me write here, where, so Q bar is I, no, Q star is I E star, and this is just opposite arrows, opposites of E, and so I can view the dual of that as the representation of this Q star quiver. Okay, that's the trick, and this also I can identify it by the trace map with GD. Okay, so let me maybe denote by a star here. I don't know. And then A star of a collection, maybe X star E, is going to be, and I'm going to get it wrong again, but let me just write it. It's just going to be the commutators. X star E, X E. Okay, over all E. And these commutators, if you think about it, they always go from one vertex to itself, because you use the arrow. If I am at vertex I use the arrow E to go to J, and then the arrow E star comes back. Okay. So this is in GD. Okay, so this is where you see this moment map appearing. Okay, it's just in the description of the cotangent complex at a point. Okay, so now we put all this together, and we can get a description for actually the cotangent complex, the cotangent of the stack. So T star rep D Q, well, it is going to be just the total space of this. So you can view this as a two-term complex over the stack rep DQ. Okay, this is a two-term complex over the stack rep DQ, and can just take the total space of that two-term complex. Let me just write it like that. E D star G D star. Okay, that's just. Okay, and if you want, you can also view it as the total space of over just the point. Well, okay. Yeah, okay. The total space over BGD of this GD mapping to, no, sorry. Yes, this is the total space. Let me just write it. No, okay. This is the total space over BGD of this T star ED to GD dual. Okay, and this is the moment map. And here I am just, over T star ED. This moment map is given by this formula over there. Okay, and finally, we can look at the tangent complex of this guy, T star rep D Q. And now you see that it is GD to T star ED to GD dual. Let's keep it like that. And okay, so this is in degree -1, 0. I mean, this is placed in degree -1, 0, 1. So you see that this has some piece in degree 1. Okay, which comes from the fact that we took the cotangent bundle of a stack. Okay, so the stabilizer, the stacky part in the cotangent bundle now becomes something that's sitting in degree 1, and so that's the derived structure. Okay, so if we want to consider the underived, the classical truncation, then we just take the zero set of this map, the kernel of this map, and this would be mu -1 of 0, and then we quotientize by GD. Okay, this is the classical truncation of this T star rep dq. Okay, so that's why it's often presented like that, mu -1 of 0 divided by GD. This is what the symplectic reduction, the classical symplectic reduction gives. I have an action of a group on a manifold. I want to understand what is the cotangent bundle to the quotient, in some sense. Then you perform this construction. Okay, but it's actually important in the definition of the product in the Coha to remember that we really truncated, and in fact, there is a derived structure. Okay, I'm not an expert in derived stuff. You should find somebody else in the room if you have some deep questions about that. But okay, so that's the description of the cotangent to the stack. So that's what we're considering. So this is, if I just look at this, then this is not smooth at all. Okay, mu -1 of 0, it's not submersive. There's no reason for that to be smooth. So the classical truncation, this is singular. Okay, this is a singular stack. But if you look at the full thing, then you see that the cotangent complex is supported in -1, 1. So it is a singular stack, but in some sense, the singularity is cut out by a certain section of a vector bundle. Okay, so it's not such a bad singularity, and this is called quasi-smooth. Quasi-smooth derived stack. And somehow this quasi-smoothness is what allows to define the product. But if you just look at this, then it can be pretty scary because this is singular. Okay, so maybe I can give some examples. Just one example. Or maybe two examples. Let's start with a quiver with one vertex and one loop. So what is the representation of dimension d of that quiver? Well, this is just, I have one endomorphism and I quotient by the group, and this is the conjugation action. So this is GLD divided by GLD. Okay, this nice adjoint quotient that people like. And then what is T star rep dq? Well, let's look at this moment map. The moment map is just a commutator. Okay, so if I look at this one, the classical truncation, let's look at the classical truncation of that, then this is the set of commuting matrices. Oops, xy in GLD square such that xy equals 0 and I quotient by GLD. Okay, this commuting matrices. And then the derived stack is just given by the commutator map. All right. So this is irreducible. It's well known that this is irreducible. Okay. Okay, and now let's look at this quiver. And let's just look at dimension 1, 1. Then, well, you see it's just A2 mod. Well, there are two copies of GM, but one of the diagonal copy acts trivially. Okay, it's just conjugation of numbers. So it's something like this. Okay, and then what is T star? Again, the classical truncation of T star rep 1, 1 of Q. So if you just write it out, it's going to be x y plus x prime y prime equals 0 divided again by gm times bgm. Okay, so it's this nice, given by this nice equation, this cone. But you can also check that this is still irreducible. Okay, and now let me introduce a Lagrangian substack in that will play an important role, which is this Lagrangian that was found by Lustig, which is the so-called nilpotent variety. And then I will tell you what it is in these examples. So Lagrangian, Lustig, Lagrangian. So yesterday I explained where these Lagrangians come from. Let me just say it in a word right now. These Lagrangians just come from the singular support of all the perverse sheaves that Lustig constructed. Okay, so it does not come out of nowhere. It comes out as a desire to study the singular support of these category of sheaves that Lustig built. So how is it defined? One point is this Lustig Lagrangian generically has no derived structure. Okay, it shouldn't, but it is singular, and at the singular points, I don't know what is the good derived structure to put. I don't know if there's a way to put a derived structure that make it Lagrangian inside the derived stack. So all I'm going to, and I don't think many people study that question. So this is going to be classical. Okay, this is going to be a classical Lagrangian in the sense that the smooth locus will be Lagrangian substack. Okay. All right, so we're looking at tuples x dual. Okay. xe, maybe xe dual, where e is in E, such that, so this is lambda. So in Lustig's original papers, he did not consider quivers with edge loops. And so he just looked at the condition that these representation of the quiver is nilpotent. Okay, so I have several vertices, and then I have some E, and here I have some E dual, and maybe here, and maybe, yes. Here I have maybe some F, and this is F dual, okay, and so on. And so the original definition of Lustig was simply that if you follow a long enough path, you get 0. Okay, but when you have quiver with loops, it's not the right definition. It doesn't produce something Lagrangian, and so it will be a little bit more complicated than that. So there exists a let's say restricted flag of I graded vector spaces. Let's call it L. So restricted means that every jump happens only over one vertex I. Okay, so this is a flag of I-graded subspaces, but any jump, the difference between LK and LK plus 1, is supported at just one of the vertices. Okay, but otherwise, it's just a flag of vector spaces such that for any k, xe of Lk is inside Lk minus 1, but xe dual of Lk is inside Lk. Okay, so we're asking that for one of the directions it is nilpotent, but for the other direction it is only stable. Okay, it's like in B cross n, something like that. Okay, and then we take the quotient by GD. Okay. Let me say lambda D, then we take the quotient by GD. Okay, so here are some examples. This quiver. Well, for this quiver, if I look at lambda D, now this is going to be the set of commuting matrices, but one of the matrices has to be nilpotent. Okay, this condition will force the eigenvalues of one of the matrices to be all 0. And so this is going to be, say, the commuting variety, but nilpotent commuting variety for GLD. And so, in fact, this is the union. One can show that this is the union for all orbits in the nilpotent cone of the conormal bundle to the orbit. Okay, so now we have irreducible components. Okay, irreducible components of lambda D are in bijection with nilpotent orbits, which are in bijection with partitions. So it's not irreducible anymore, and we have some nice set of irreducible components. And just one observation. You can also write this, if you want, as, well, you can write rep D of that quiver. You can write it as the length D coherent sheaves on A1, if you want. And then this T star, rep D of the quiver, you can write it as length D coherent sheaves on A2. And this lambda, you can write it as length D coherent sheaves on A2, but supported on A1. Okay? And so this maybe explains the Lagrangian, that it has the right size. Okay? Sorry? Set theoretically supported. And if you wanted the nilpotent, really nilpotent version, this would be length D, but set theoretically supported on 0 in A2. And that would be irreducible, but too small. OK, so this is the example. And the other example. And the other example, so if you look at rep, I erased it. So rep 1, 1 of Q, if you remember, this was A2 mod GM, okay, times BGM. So inside of this, we have P1, and then we have, okay, it's not a disjoint union, but we also have a BGM. Okay, we have an isolated point. And if you look at lambda, then this nilpotency condition will force either two of the maps in one direction to be 0, or two of the maps in the other direction to be 0. Okay, otherwise it won't be nilpotent. And so this is going to be the 0 section, rep 1, 1, Q. 0 section, and if you want, it's just the Zariski closure of this P1. Okay, so you can say it's the Zariski closure of P1. Union, let's say rep dual 1, 1, Q. So the other two arrows are going to be 0, and you can say that this is A2 bundle sitting over the BGM, okay, in this stack. So when you take so it's something like this. I have P1, and then in the closure I have this point. I have this BGM, and when you look at the cotangent bundle to that, okay, so it's a big thing, but there's a Lagrangian, which is this irreducible component union this irreducible component. Okay, so we have two irreducible components. And in general, if you take an equiver and you look at this Lustig Lagrangian, you have some beautiful combinatorics describing all the irreducible components. And there's a nice inductive process to construct all of these, which is called this crystal graph, which hinges on the same kind of induction argument that are used to prove Lustig's theorem about k equals k prime. Okay. So let me state the theorem. So the first theorem is that lambda is Lagrangian. Again, it means generically Lagrangian. Okay, so that's not an obvious theorem, but that's the theorem. And the second statement is that this characteristic cycle map is an isomorphism from the specialization V equals -1, if you remember the notation of this category of perverse sheaves, Lustig perverse sheaves, graded Grothendieck group, to H top of lambda, which is just a vector space spanned by irreducible components. Okay, C, irreducible components of lambda. Okay, so this is due to Lustig, and this is due to Kashiwara and Saito, but there are many Saito. This is Yoshihiko Saito. Okay. So maybe I can say the rough idea of the proof. Both of them follow. Let me just say that both proofs use the inductive structure of lambda, which is coined in this Kashiwara crystal structure. Okay, so Lustig found this Kashiwara crystal structure in the perverse sheaves, but it's the best way to see it is in this irreducible components of this Lagrangian. And okay. So as a corollary of all that and the Katz conjecture, as a corollary, we get that the dimension of H top, so the number of irreducible components in lambda d, if I put them all together, sum over d, z power d, I get the platistic exponential of the sum over d of the value at 0 of this Katz polynomial. Okay. So now we're very happy because this Katz polynomial, just a constant term, arises in this combinatorics as the h top of lambda d. And now we can look at all the other cohomological degrees. And the nice thing, beautiful thing that you can expect is that this will construct all the other coefficients of the Katz polynomial. Okay. So the question now is compute, well, the Poincaré polynomial of lambda d, the full Poincaré polynomial of lambda d, also the full Poincaré polynomial of just the full stack. You know, there's no reason to forget that full stack. Yep. So the theorems will be that these will be related directly to the full Katz polynomial, but I want to explain the strategy of the proof. The proof are, you know, involved, but still, I want to explain the strategy. So, strategy. Well, if we want to relate it to this Katz polynomial, Katz polynomials, they count points over finite fields, right? In some sense, they are count isomorphism classes of objects, which is the same thing as counting the volume of a certain stack over FQ. And so we have to, at some point, go from characteristic 0 to positive characteristic. And so the idea is to use some purity, cohomological purity results, and point count over FQ. Okay, so I will state the purity results for the Borel-Moore homology of these things, or compactly supported cohomology, and then I will try to explain what the point count, how you perform the point count, at least in one case. But the purity results are, a little bit hard, so I can say some words and give you references, but certainly not give the proofs. Okay, so here are the theorems. So before, let me say the following remark. So, for every edge E, in E there is an associated GM, an associated one parameter group acting on rep dq by rescaling that edge. Okay. Okay. And so this leads to a big torus T, which acts on rep dq and also on the tangent. So this is GM times the cardinality of E, which acts on T star rep Q. Okay, for any D. Same torus acts for any D. And of course, there's an action on the dual torus. Okay, but what you want is just to make sure that the moment map equation is preserved, so it's homogeneous. Okay, so you can choose the action on these in however way you want, and then you get the dual action on the dual space, but you're also allowed one more freedom so that the moment map remains homogeneous. Okay, and so it's a good idea to consider T-equivariant homology. So for the top part, it will not matter because the T-equivariant homology only changes the lower part, not the top dimensional part of the homology. But yeah, it's still important. Okay, so maybe I state the theorems above then. So let's just work with complex coefficients. So if I look at the T-equivalent Borel-Moore homology of this Lustig-Lagrangian, then this is pure, cohomologically pure, and even, and free as a HT module. Okay. And then the same thing for rep, for T star rep Q. This is pure. Yeah, I think it's everything the same. So the first one is due to myself and Vassereau. And the second one is due to Ben Davison. So the proofs, so the second one is true in much more generality. Okay, so Ben has theorems that apply to any two Calabi-Yau category with some finiteness condition that are satisfied here. And I think, so our results for lambda appeared before, but I'm pretty sure that they can be also deduced directly from Ben's result. So our proof is very specific to this lambda, and it uses Nakajima quiver varieties that you can realize as a compactification of these lambda. And you can deduce the purity, the evenness, and even the free as a HT module, because you know the same holds for the Nakajima quiver varieties. So the one, we embed this somehow partially compactify into a Nakajima quiver variety, and then we deduce everything from there. And here, this uses some more advanced tools that maybe Lucien explained a little bit yesterday in the exercise session, so essentially, maybe it's really beautiful. So I'm just going to say a few words, just a few words. So for 2, just roughly the idea, okay, very roughly. So this stack rep Q, okay, the homology, actually the stack itself, but let's say the homology of the stack, you can relate it to the homology of some moduli space, moduli stack, and the critical homology, maybe it's a critical homology, of some moduli stack of objects in a certain 3 Calabi-Yau category, which is obtained from this by essentially adding in addition an endomorphism of this representation of the double quiver. Okay. And this is by something called dimensional reduction. And then you use, again, the dimensional reduction to relate this to the homology of a stack which almost looks like this one, except that now it's going to be the stack of pairs x and maybe phi, such that x is a representation of the quiver, and phi is an endomorphism of x. Okay, and now this stack you can stratify according to the eigenvalues of this endomorphism. Okay, you can break it down into, there's a nice stratification, and you can reduce everything to the nilpotent case. So this stack, the set of pairs x phi, x is in rep q and phi is an endomorphism of x, has a, let's be a bit vague and say a nice Jordan stratification. Okay, this according to eigenvalues, and you reduce to the nilpotent case, and in the nilpotent case you have the Jordan stratification, actual Jordan stratification, and all strata can be expressed just in terms of some rep d prime of q. Okay, so once you perform this, cutting up, chopping up into pieces, at some point you get into something which is like a product of stacks of this form, and these are all very nice and pure. So through this fancy tool of going through 3 Calabi-Yau categories, you can get some this type of purity results. Okay. All right, I have only a few minutes, so let me just give the point counts, theorems concerning the point counts, and maybe prove one of them. Okay? Because today I did not prove anything, like yesterday, actually, but I want to at least explain one way that we can see that the relation to counting isomorphism class of indecomposables and counting points on these varieties. So point count. So here's the theorem. So now we are actually considering these varieties over FQ, and we are doing the point count. So the first is that the sum over D of the cardinality of T star rep D over FQ, QDD Z to the D is given by the platistic exponential T minus 1 sum A QD of T Z to the D. And then after that, you put T goes to Q. Okay, and this is platistic exponential with respect to T and Z. Okay, so this was proved by Mozgovoy. And the proof is very nice and simple. And then the second statement, maybe I can write it just down there, is about this nilpotent case. Exponential 1 over T minus 1 times the sum AQD T minus 1. 1 over 1 minus T minus 1, sorry. ZD T equals Q, and here we actually need a small variant of the Katz polynomial. Okay. And this one was proven by Bozek, myself, and Vassereau. Okay, and so to finish, I have 10 minutes. Okay. Okay. So let me give an idea of the proof. Actually, let me give the proof of one following Mozgovoi. So, yes, okay. So maybe first I should say that T star rep D of Q, this can be identified with the set of pairs X, and instead of considering some dual operators, okay, satisfying the moment map condition, I'm going to interpret in representation theoretical terms this thing. So what is this? This is a point here and a cotangent vector. Okay, so a point here, the tangent space to a point here, okay, is well known to be the x1 one. Okay, x1 of the of mm, x1 mm at a point. And so here I'm looking at, let's say, the pairs of representation m and phi, which is in x1 mm dual. Okay, and then, of course, I quotient by the group G. Okay, so it's badly written. Let me say, yes, m as an element in ED, okay, and then an element in x1, and then I quotient by GD. Okay, so this is another way of interpreting this moment map. And so what I want to count, so the sum over D of T star rep D over FQ, Q power DD Z power D. This, in fact, is the sum over all objects of the cardinality of x1 mm, okay, divided by the group of automorphism of m. And here I have a q mm and z power dimension of m. Okay, this is the way to interpret this point count over, where m here is, of course, up to isomorphism. Okay. Now you have the Serre, not the Serre, the Euler form.
Sorry, where is the FQ point information in this last line?
So M runs over all FQ representations. Okay, so now you have, by definition, minus the Euler form is the dimension of x1 m minus the dimension of endomorphism of m. Yep. So I can replace this q to the dimension of x1 by minus m plus the dimension of endomorphism of m. Okay, so now we are all of a sudden into a sum that looks a bit nicer. It's the this q power mm disappears, and now I have the number of endomorphisms of m divided by the number of automorphisms of m, z to the dimension of m. Okay. So this almost looks like it's a big sum of something close to 1, right? Because endomorphism is just a little bit bigger than automorphism. And if you again do this platistic game, so maybe I just say that this thing here can be computed from the decomposition of M into indecomposables. Okay, so yes, if M is indecomposable, then you can quotient out by the radical, and M over the radical is going to be a finite extension of FQ, and then the degree of that extension is exactly what the platistic exponential treats, and so the difference between the two is just going to be the number of points in that field extension, the units in that field extension, something like that. Okay, the number of points in that field divided by the units. So it's going to be a combinatorial sum that only depends on the number of indecomposables and how these indecomposables decompose over the algebraic closure. Okay, so you can look in the Moscovo's paper or in other papers for the way the platistic exponential treats that, but then from that you will get something like the platistic exponential of the sum for all d of t over t minus 1 times the number of absolutely indecomposable representations of dimension d. And this t over t minus 1, really you should think of it as endomorphism divided by automorphism. Okay, A1 divided by GM. And there is a z to the d missing. Okay, but so the point count, what I want to say is the point count of the number of elements in this cotangent stack here is in fact very easy, and it just follows from properties of categories of global dimension 1. Okay, you just have the Euler form, and maybe you need to know that the automorphism group are connected or something like that, but that's it. And then with the help of the purity results, from that you can deduce at least the size of these algebras. And I did not have at all time to define the algebra. I will do it tomorrow. Just today we saw the size of the algebra.